another metastable or non-equilibrium process, one of the advanced processes which is used to generate a number of novel materials. This is called mechanical alloying. As the name suggests, this is a way to bring two metals or two elements into the form of an alloy by mechanical means. So this is nothing but basically a high energy ball milling process, where you take pure metals A and B, put them in a ball mill, and then allow the two metals to come together to form an alloy. This field, if you look at this view graph, this field is basically started with a person by name J.S. Benjamin in 1966 at the Paul D. Merica Research Laboratory in US, where they wanted to generate nickel coatings on the thoria. There was a lot of work going on those days to somehow incorporate the thoria or yttria into the nickel based superalloys to give the high temperature strength for these superalloys. We know that most of the superalloys they get their high temperature strength from two basic components. One is the ordered intermetallic, which is called gamma prime Ni3Al, which is present in the nickel base. So you have an FCC nickel base matrix in which you have Ni3Al ordered FCC particles which are embedded in the nickel base matrix, and that gives you very high strength. But we know that precipitation hardening does not really give you strengthening at very high temperatures, because the moment you go to very high temperatures, you have either coarsening of the precipitates which occurs or dissolution of the precipitates. This is a typical problem with any precipitation hardening. But there is a small difference between Ni3Al precipitation strengthening, because Ni3Al, it is known that it gives you an increase in the strength with increase in temperature, at least within a small temperature domain of up to around 900 degrees or so. But if you want to use these materials beyond this temperature, it is very difficult to use them, because at these high temperatures these precipitates will either dissolve or coarsen. As a result, what we see is people have thought, instead of having only the Ni3Al particles, if we can put some dispersoids which are oxide dispersoids such as yttria or thoria, one can have much better strengthening at high temperatures. And when they were putting these yttria particles into the nickel based super alloys, they found that the wettability is very poor. So in order to improve the wettability, they thought if they can coat it with nickel, they can improve the wettability. The way to coat it, they thought, could be a ball milling technique, where ball milling has been used for quite some time. Even in metallurgy, we know that most of the ores, once we take it out from the earth's crust, we break them using a ball mill to make them finer sizes, so that they can be loaded into a blast furnace or something like that, any furnace. Further reduction. So as a result, they thought they will use the ball mill to coat nickel on the thoria or on yttria. So they were quite successful, and then they thought, why don't we straight away make the ODS nickel based superalloy. What is ODS? Oxide dispersion strengthened. That means yttria or alumina or thoria, any oxides. So you disperse the oxides into the nickel based superalloy. That means instead of first coating the compound with the pure metal such as nickel and then putting it into a melt of nickel based superalloy, which is a two-step process, instead of that, what they decided is to let us take all the elements which are required for the nickel based superalloy, put all of them into the ball mill, along with that put all the oxide powders, so that you ball mill all of them together. When you ball mill all of them together, you can end up ultimately into a superalloy containing these fine dispersoids, and that gives you very high strength. So this was the origin of this whole thing, and the actual term mechanical alloying was not given by Benjamin, but a patent official, his name is McQueen, he basically thought, let us call it as a mechanical alloying, because you are making the alloys using mechanical means. So that was an idea which has been given by the McQueen. So if you look at how this whole field has evolved, if you look at the first experiments on mechanical alloying are around 1966, as you can see here, and then the first patent in mechanical alloying came around 1972, and commercial alloys have started around 1974 or so, and the first pilot plant has come up around 1975. And then you have some interesting things that have taken place. For example, amorphization by mechanical alloying, all metastable materials. In fact, before 80s, they are all basically stable materials. People have never really thought that we can use mechanical alloying to produce novel metastable materials such as either nanocrystals or quasicrystals or amorphous materials. So the first experiments were 1983, amorphization by mechanical alloying, and almost the same year amorphization by mechanical milling. What it means is that you take a compound, keep on doing ball milling, and the compound, ordered compound, transforms into an amorphous. First it becomes disordered and finally it becomes amorphous. So instead of doing mechanical alloying where you take elements A and B, whenever we take two or three or more than one element and then put it into a ball mill and then do ball milling, we call it as a mechanical alloying, because you have individual elements there. But if you take a pre-alloyed powder, that means an alloy which is already made into a form of an alloy by some means, by melting and casting route, and put that alloy powder into a ball milling and do the ball milling, we just call it as a mechanical milling. So this is the difference between these two, and people have shown that even pre-alloyed powders, intermetallic compounds, can be made into an amorphous. And nanocrystals by mechanical alloying has come around 1987. Quasicrystals by mechanical alloying also almost 1988. Reactive milling has started around 88-89. Then mechanical alloying in immiscible systems, that means systems where the A and B do not dissolve into each other under the normal conditions. For example, there are a number of systems which are monotectic systems. We know in the phase diagram there is a miscibility gap in the liquid itself. That means A and B do not dissolve even in the liquid state. Even such alloys can be made into an alloy by mechanical alloying. We will talk more about it later. So all this has happened before 90s. So this field has more or less got matured by 90s, and after 90s now there is a lot of work going on trying to understand the process, because before this the understanding of the process was not really much. So what is the energies that are going into and how these energies are affecting the process, and so is there any correlation between the energies that we are putting in and the phase that is coming out. So all this kind of fundamental understanding has come in the last 1 decade. If you look at what is this process, the process is basically composed of two basic processes. One, when a ball like this, a section of the ball is shown here and another ball is shown here, two balls, if they are hitting powder particles, what happens is two processes occur. One is a fracture of the particle, it is a breakage of the particle. Second is cold welding of the particles. When a particle breaks, depending on the type of particle, if it is a ductile particle, it becomes like a flake. Whenever a ductile particle is hit by a ball, it immediately becomes a flake, and that flake, if it comes across another flake, because it has a large surface area to volume ratio, a fresh surface is exposed, so immediately there is a tendency for the welding to occur, and as a result you can see here a pancake type of structure happens, like a sandwich kind of structure. So you can see layered structures. This is a schematic diagram, and this is the actual picture of one such system. This is a titanium aluminum system where you can see layered structure within one particle, and this layered structure, if you carefully observe in a backscattered image in SEM, it shows you the white and black contrast, which clearly tells you the compositional contrast. One is the one of the elements, white is one element and dark is another element. So which basically tells you this comes because of the atomic number contrast. So whichever has a higher atomic number, that will look brighter. Okay. So, this is how we can find out that there are different elements and alternate layers of these elements take place. And once you get that kind of things, alternate layers, any phase can form. We will come to what are the phases that can come out of such a mechanical alloying. Before that, let us look at what are the types of mills that we use. One is called a vibratory mill. These are typical laboratory mills. There are two laboratory mills which people use usually. One is called a vibratory mill, which is where basically you take a box in which you put the powder and the balls and then shake it at a very high speed, something like 50 cycles per second. So, almost about 1200 RPM if you want to convert it into an RPM. So, you can have such high frequency impacts, because in each vibration there will be one impact at least. So, balls impact the powder, and because of which you get. So, this is a commercial ball mill called Specs mill. This is an American mill which is very often used, but the only problem with this mill is the quantity of the powder that you can use is very small, not more than about 20 grams. So, if somebody is interested to make slightly larger quantities, he cannot use this kind of mill. The next ball mill which is very popular is what is called a planetary mill. This is one such planetary mill where you see a disc. The schematic picture is shown here. You have a disc there. This black one that you are seeing here is a disc, and on that you see 4 white colored jackets, and these are called bowls or vials, and these bowls rotate in a direction opposite to that of the disc. The disc rotates in one direction and the balls rotate in the opposite direction, and that is why you can see the disc is rotating in this direction. This is the rotation of the grinding bowl, and the movement of the disc is shown in the opposite direction here. And because of this, the balls which are there inside the bowl will get some kind of a centrifugal forces, and because of this the balls will hit the powder, and hence you get the energy transferred to the bowl. And this kind of ball mills, planetary mills, are slightly having a higher capacity than the vibratory mills, and one can go up to about 1 kilo. If you put 4 bowls, each one can take around 200 grams in principle. It depends on the type of materials and the density of the material, because the volume is usually fixed. So, depending on the density of material, one can go up to around 200 grams per bowl. So, approximately about 1 kg one can get. So, this is the laboratory mills. Now, let us come to the commercial type of ball mills. Commercial type of ball mills, one ball mill is called an attritor mill. An attritor mill is something similar to a drilling machine. Basically, you have a motor here and a shaft, and this shaft, in fact, the first attritor mills, wherever you go to any lab where you see attritor mill, they have basically converted a drilling machine into an attritor mill. So, what you have, this whole thing that you see here, this whole thing is nothing but a drilling machine. And what in a drilling machine you have a shaft where you put the drill bit, isn't it? So, here instead of a drill bit, what you do is to that shaft you put some horizontal rods which are called impellers. You put horizontal rods to that shaft and then put a container here. This is a container, and that container consists of the balls and the powder. And so, when you are rotating this shaft, the impellers also move, and once the impeller hits a ball, that ball goes and in turn it hits a powder particle. There is a probability that a ball will hit a powder particle. So, at the same time there is also a probability that the ball will hit another ball. So, some energy is lost between ball to ball interactions, but at the same time some of the energy also is transferred to the powder. So, as a result you get some transfer of the energy, and finally the powders get converted to either nanocrystals or quasicrystals or intermetallics or amorphous phases or anything that you are interested, depending on the total energy that is transferred. So, this is one type, and here you can in principle go up to about 5 kilos. This is a very common commercial mill, but the energies here are usually lower than what you get either in the Specs vibratory mill or in this planetary mill. So, the laboratory mills usually have the highest energy, and this is another mill which is a typical mill that every metallurgist knows, what are called tumbler mills. In a metallurgy, what is called ore dressing subject, if you have ever read in your BTech you would have come across these tumbler mills, because we talk about these tumbler mills where the ore which is taken out from the earth's crust is broken into smaller pieces, and that is what we use this. So, basically you have two rollers on which you put a drum, and that inside that drum you put your balls and the powders, and when you operate this drum at the critical velocity, very close to the critical velocity where the balls will pin to the wall of the tumbler mill. So, just lower than that velocity if you use, then the ball will go up to the top and then just falls from top and then gives you an impact. And here also, depending on the size of the actual container, one can have the energy is decided by that, because the height from which the ball drops is what is going to give it the kinetic energy to it. So, as a result, the energy of this mill depends basically on the diameter of the ball, and at the same time it also depends on the speed at which the whole tumbler mill is rotating. So, you can see here a series of such tumbler mills. This is a picture from Inco Laboratories, International Nickel Company, USA, where they have really made commercial mechanically alloyed products from the elemental powders. All superalloys have been made in this kind of ball mills. So, here you can really have about 200 kilos without any problem. Only problem is whether the energies are high enough or not. So, whether we can use this kind of mills to produce either nanocrystals or amorphous materials or not is something which is what people are studying nowadays. In fact, within 15 days we have a small workshop on just to discuss that aspect, whether we can produce such ball mills which are commercial ball mills, high scale ball mills, where the energies can be as much as you can put into these laboratory mills. So, if so, how to design such a ball mill where the similar energies can be imparted. So, there is a workshop going on that. So, hopefully people will come up with some idea. So, the other type of ball mill is what is called a uni ball mill. This is a special type of ball mill which is different from the other ball mills, in the sense here the actual energy is imparted because of the magnetic magnet which is kept here. So, you have a tumbler kind of mill here, circular or cylindrical shaft in which you put balls and you put a magnet here. So, now depending on where you place the magnet and start rotating the bowl or start rotating the container, and the balls are taken to a higher position depending on the position of the magnet. If the magnet is exactly at the bottom, then definitely balls will not go to very high, because the magnet is attracting these balls, and these balls are basically steel balls. So, steel balls are attracted by the magnet. So, the balls will not go to very high position here, and so basically they will keep on moving there itself. So, there is not much of impact, but only some shearing process will take place. So, one can control the type of the mode of energy transfer, whether it is just a shear or an impact kind of energy. So, one can change this energy mode by changing the position of the magnet, and that is why we call this as a low energy mode and a high energy mode. So, if you put the magnet at some position somewhere here, let us say, you will get much higher energy. So, like that one can control this. So, either shear mode or the impact mode. So, here also one can have large quantities produce something at least about 5 kilos or so. One can produce this kind of a large quantities in this. So, these are the typical types of mills that we use. And now, let us come to what you can achieve by this kind of mechanical alloying or milling process. If you look at the mechanical alloying or the milling process, basically it is a defect induced process. You are introducing a lot of defects into the system, breaking the powder particles into finer and finer particles, and during this fracture process you are introducing a lot of defects such as dislocations, vacancies, all kinds of defects are generated, and because of these defects that you are putting, the phase formation or phase transformations are enhanced, because the diffusivity is enhanced. In fact, people talk in terms of a special type of diffusion called pipe diffusion. Have you ever heard of pipe diffusion? If you have gone through a diffusion process, diffusion course, you would come across this. A pipe diffusion is a diffusion through dislocations. A dislocation is what? Is nothing but a row of vacancies, isn't it? So you can imagine a dislocation as nothing but an empty pipe. It's like just a cylinder which is an empty cylinder, like a tube. So you can imagine a dislocation as a tube. So where the diffusion can occur very fast. So if you have a large number of dislocations inside a material, so diffusion can occur very fast. And at the same time, when you are decreasing the size of the crystals, we know diffusion is always basically a phenomena which is driven by two things. One is the diffusivity, another is the concentration gradient. In fact, we should not call it as a concentration gradient, we call it as potential gradient. For a binary system, a potential gradient is equivalent to the concentration gradient, not potential gradient in principle, it is chemical potential gradient, whatever it is. We talk about only chemical diffusion, so we do not talk about any electrical diffusion or so. So here potential is not a voltage potential, but it is a chemical potential. So dC by dx is equal to d mu by dx in principle for a binary system, but for a ternary system it is not so, ternary or quaternary system. So let us consider it is, so it is a function of two things. The flux is diffusivity and concentration gradient dependent. So diffusivity depends on the temperature, we all know basically, and also the concentration, of course, because diffusivity we can think of as a concentration dependent or concentration independent when we try to calculate it. All of you have gone through diffusion course any time at some point of time, or a part of metallurgy course, some metallurgy course you must have come across diffusion. Anyway, so fixed laws you must be aware of. So basically diffusivity is more or less, people take it as temperature dependent process, where d is equal to d naught into exponential minus q by RT. So where temperature comes into picture, q is called activation barrier for diffusion and d naught is what is called the pre-exponential tau. So now dC by dx is very crucial in this kind of situations. When you are decreasing the size, let us assume that in a ball milling you are forming alternate layers like this, A and B. If you are doing continuous milling, the thickness of the A and B keeps on decreasing, because there is a continuous breaking and again rewelding taking place. So because of which there is a continuous decrease in the thickness of individual layers, and if there is a continuous thickness decrease, then you can see what is called the dC by dx increases tremendously, because the dx is decreasing. As you can see, the dx is nothing but the diffusion distance, the distance over which diffusion has to occur. In a layered structure like this, the diffusion has to occur in this thickness, isn't it? So if that thickness can be reduced, then the dx is decreased, and if the denominator decreases, then the whole fraction increases tremendously, and as a result the flux increases. So that is one of the reasons why you have the defect induced phase formation and transformations which gets enhanced because of the defects and the decrease in the size of the crystals that occurs during ball milling. And because of this, you can have either stable phases forming and metastable phases forming at room temperature. This is very crucial. All these phases are not really happening at high temperature, they are all happening at room temperature or close to the room temperature. We will talk about the temperature during ball milling at some point of time. Okay, so you can take it granted that more or less temperature is close to the room temperature. So all these processes occur at near the room temperature. So and what can happen? As I told you, it can give you nanocrystals, it can give you nanocomposites if you are putting more than one type of material. So you can have nanocomposites. For example, if you take nickel based alloy, so nickel and yttria, if you take it, you can break it to very fine size, and ultimately if the energies are very high enough, you can make a nanocomposite of nickel into which you can have yttria. So you can make nanocomposites, and you can have what is called alloying, and because of that alloying you can have extension of solid solubility. Rapid solidification processing, we have talked about extension of solid solubility. Similarly, here also we have extension of solid solubility. In rapid solidification processing, the concept which tells you about extension of solid solubility is the T0 concept. We have talked about T0 concept. Here we are forcing the atoms to come together and form an alloy. So that is why we call it as a mechanical alloy. You are mechanically bringing the A and B atoms to come together and form an alloy. And so that is how you can have large extension of solid solubilities. We will come to each of these one by one, and one can have alloying in the immiscible system. This is one thing which rapid solidification processing cannot do it, because rapid solidification processing, you are starting with what? You are starting with liquid. Your starting material is liquid. If in the liquid, if the two elements do not dissolve, then you can't help it. So if the two elements have not dissolved in the liquid state, then you cannot have solubility of A and B in the solid state, because you are already starting with two liquids, and those two liquids, if you are cooling it fast, those two liquids may give you two solids. So ultimately you end up in two solids instead of one single solid, whereas here it is not such a thing, that even if the two elements are immiscible in the liquid state, you may end up in a solubility, and in a number of systems people have really ended up in a good solubility in such systems. We will give you examples of that also. Then one can have disordering. Before that I should say, one can make intermetallics after alloying. After solid solution formation, the next possibility is intermetallics. One can make intermetallics, whether they are crystalline intermetallics or quasi-crystalline intermetallics. We have talked about this at some stage when we are talking of nanocrystalline materials. One can have disordering in the intermetallics. One can take an ordered intermetallic, make it disordered. I told you why we want to make it disordered, because a disordered compound is more ductile. So if you want to introduce some ductility into a compound, if you can take an ordered compound and put it into a ball mill, one can make it disordered, and one can make it completely amorphous, and one can also introduce chemical reactions. So these are all one can do, and these are some of the examples. Nanocrystals one can make. This is in the metallic system, this is in the oxide system, PZT, and the nanocrystal, the crystal size that you can achieve by mechanical alloying is always a function of melting point. The higher the melting point, for example graphite, tungsten have a very high melting points, one can achieve very low crystal size. Whereas if you take aluminium, copper, silver, they all cannot have very high, very low crystallite size. You have a high crystallite size. That is one. Coming to alloying, alloying basically occurs by two different processes. I said continuous diffusive mixing and discontinuous additive mixing. Sometime we have talked about it. This is an example of such a continuous diffusive mixing. Here lattice parameter of copper and nickel is plotted as a function of milling time. You can see one of them, the lattice parameter decreases, another lattice parameter increases, and at some point of time they become same, and that is the time when the alloying has taken place. Similarly, this is germanium silicon, this is germanium, this is silicon, one increases, another decreases, and finally you get an alloy. And this is tells you how much solubility you can achieve. This is iron copper. Iron copper is supposed to be an immiscible system. A lot of people are working on these immiscible systems now, particularly to put a small amount of copper into iron. Interstitial free steels, lot of people are working where they want to put small precipitates of copper, particularly nano crystalline copper, into iron, so that they can increase the strength of the interstitial free steels. So if you look at what is the equilibrium solubility, is only 0.3%. Only 0.3% of iron can go into copper under equilibrium conditions. By rapid solidification one can go 20%. By evaporation 35%. By sputtering about 50%. By mechanical alloying one can go to 68%. You can imagine from 0.3 you are going up to almost 68%. So this is all because you are just forcing the atoms to come together. So that's an advantage of mechanical alloying. And similarly, I told you earlier, nanocrystallization is a prerequisite to alloying. We have talked about it when we were talking about nanocrystals. I thought we will just bring it here because this is something to do with mechanical alloying. So when the crystal size decreases to a critical value, suddenly the solubility occurs. This is true whether it is a copper zinc system or copper nickel system, or this is iron silicon system. So, the solubility of silicon in iron suddenly increases when the crystal size comes below 20 nanometers. Up to 20 nanometers there is no solubility, beyond that suddenly, below that suddenly there is a solubility. So, this we have already talked sometime, and then discontinuous additive mixing is another which we talked. So, this is another mode of alloying which occurs during mechanical alloying in case of ordered compounds, not for solid solutions, but in case of ordered compounds with high negative enthalpy of mixing, you get this kind of discontinuous additive mixing. And one can have extension of phase fields in the intermetallics also. We talked about extension of solid solubility in solid solutions, but one can have extension of solid solubility in intermetallics. For example, NiAl is one such example, where equilibrium conditions you get a solubility from 45% to 55%. Here you can get from 25% to 65%, a very large extension, and it is all because of nanocrystals. And one can show that when you make it nanocrystal, the phase field becomes much larger. This is very easy to show. And one can introduce disordering, but the extent of disordering that you can introduce into ordered compounds depends on the ordering energy of that compound. How ordered is that particular order? Because some of the, if you compare some intermetallic compounds, for example, let us take beta brass. Beta brass, if you start heating beta brass, it is ordered at room temperature. Once you cross a particular temperature, what temperature is that? About 450 degrees centigrade, it becomes disordered. Whereas NiAl, if you take it up to the melting point, only at the melting point it becomes disordered and melts. So, it does not become disordered up to the melting point. So, because the ordering energy is different for different ordered compounds. So, if you look at it here, this is one example, Ni3Al, copper titanium, cobalt zirconium, 3 different ordered compounds have been ball milled. As you are increasing the milling time, the order parameter, long range order parameter decreases. In one case it continuously decreases and becomes 0, in one case it decreases and more or less reaches a saturation, below that it does not decrease much, and in one case it does not decrease at all, because this is a very strong ordered compound. So, it is very difficult to introduce disorder into some strong ordered compounds. NiAl is one such compound. Ni3Al can be made very easily disordered, but NiAl cannot be made disordered. Similarly, if you look at an ordered phase and start increasing the temperature, we know usually there is a temperature at which it becomes disordered, and if you start increasing this temperature further, it becomes liquid, isn't it? Sometimes in some cases this disordering temperature and the melting point both might be overlapping with each other in some kind of compounds. In case of copper zinc kind of beta brass, this temperature, there is a difference in this temperature, because the melting point is different, the disordering temperature is different. So, similarly here there is an analogy between the temperature and mechanical energy. If you keep on increasing the mechanical energy, the ordered phase becomes disordered, and this disordered phase, if you keep on increasing the mechanical energy further, it becomes amorphous, which is similar to that of the liquid. So, this is something similar to what happens if you keep on increasing the temperature. An ordered phase becomes disordered and becomes liquid. So, instead of liquid, in a mechanical energy it becomes the amorphous. So, that is one way one can do. And one can talk in terms of what happens when you put these powders into a ball mill and look at how various milling parameters affect the type of phases that are forming. This is one such example which tries to show you different milling parameters. One is called, in ball milling, the different milling parameters. One is the speed of the mill, the RPM, and the ball to powder weight ratio. So, if you are increasing the speed of the mill, definitely you are increasing the energy, isn't it? And if you are increasing the ball to powder weight ratio, that means for the small amount of powder, if you have more number of balls, then the possibility of a ball hitting another ball increases. That is one possibility. At the same time, there are less number of powder particles which receive impacts. So as a result, the possibility of each powder particle receiving more impacts also increases, and because of which the energy, total energy transferred to the powder over a period of time increases. As a result, the higher the ball to powder weight ratio, the higher the energy transferred. But at the same time, there is a critical limit, because if you keep on increasing the ball to powder weight ratio, then the number of balls have increased to such an extent there is no ball to powder impact at all. All ball to ball impacts will take place. So ultimate effective energy transfer will come down. So there is an optimum level. We have done a lot of studies on that. This is one such example where you can see the time required for amorphization keeps on decreasing as you increase the speed 200, 250, 300 RPM, and as you increase the ball to powder weight ratio, and this is for two different systems. And similarly, one can put the RPM, ball to powder weight ratio, and the time required for amorphization, all of them together, and see basically similar results. And again the time required for amorphization, if you look at for various systems, one can see that at very high milling energies, that means high ratios and high RPM, the overall time required for energy for amorphization is the same irrespective of the system that you choose. When you are putting in so much energy, every system becomes amorphous very easily. So whether it is a easy glass forming system, as I told you, if you use a laser for rapid solidification, even a pure metal can become amorphous. So whether it is a easy glass former or a non-easy glass former, both of them will easily become a glass when you use a very high cooling rates of the order of 10 to the 12 or 10 to the 14. Similarly, when you are putting very high energies, whether it is a easy glass former or non-easy glass former, if for example here when you are putting small amount of energy, the easy glass former will take less time, a glass which is not a easy glass former will take more time. But when you are putting very high energy, all of them more or less take very low amount of time. And one can put all these into energy parameters. There are basically two energy parameters during ball milling. One is called impact energy, which is called EB, ball impact energy. That means when a ball is hitting the powder, what is the energy of the ball? How do we know that? It is nothing but half mv square. The impact energy of the ball is nothing but half mv square. So, and if we know the mass of the ball, if we know the velocity of the ball, one can calculate half mv square. And in addition, one has to consider also ball to ball impacts, because some energy is lost when a ball hits another ball. So because of which the effective energy transferred from the ball to the powder is decreased. So because of which we multiply with a parameter called phi, and that is decreases the overall impact energy of the ball. So this EB star is nothing but the effective impact energy of the ball, and one can calculate phi b very easily depending on the extent of filling of the container and the ball to powder weight ratio and things like that. And the total energy of the ball is crucial. Total energy of the ball is nothing but the impact energy of the ball, number of balls, the frequency of impacts, and time of milling. All of them will come in the numerator, and the weight of the ball, weight of the powder comes into the denominator. That means if you put large amount of powder, then the total energy transferred for each powder particle obviously decreases, because there are too many particles to receive the impacts. If you have less number of powder particles, then less number of particles are receiving more impacts, so each particle receives more number of impacts. So as a result, the total energy transferred to the powder particle is more. So like that, one can put these two energy parameters and try to look at bring in all the milling parameters into these two energy parameters and look at what happens. When you plot these two energy parameters, y-axis the impact energy of the ball, x-axis the total energy, and try to see under what conditions you get an amorphous phase. You see that irrespective of the impact energy, there are 3 different or 4 different impact energies here, different levels of impact energies, and at each impact energy the total energy is increasing in this direction, and you can see that there is a critical value of total energy beyond which the amorphous phase forms. Below that it does not form. You can see this is copper, titanium nickel, this is titanium copper. So you can see below this particular, if you put a vertical line like this, below that line all are white circles, they are, that means they are crystalline, they have not yet formed amorphous, and beyond that line you have amorphous phase formation. That means there is a critical energy beyond which they, so the actual impact energy of the ball is not crucial. What is the total energy transfer to the powder over a period of time, that is crucial for any phase formation. And one can do this for various glasses. This is another ternary kind of a glass where a nanocrystal becomes a glass after certain period of milling, and again here also you can see there is a minimum total energy beyond which you get a glass. But interestingly you can see that here also you see these half filled circles means that the amorphous phase that has formed in this domain crystallizes when you put very high energy. This is also another interesting thing. If any amorphous phase that forms is not a stable phase, it transforms into a crystal when you heat an amorphous phase, because we know whenever a glass is heated, a glass becomes a crystal. So if you heat this glass, it becomes a crystal. So similarly, when I am putting in more and more energy, more and more defects are coming into picture, and these defects enhance the diffusivities, and because the diffusivities are so enhanced, so crystallization can occur very easily even without increasing the temperature. So the amorphous phase can become a crystal in situ in the ball milling itself without taking it out and heating it into a DSC or doing an annealing. So this is kind of in situ crystallization. So one can do all that, and one can also show that there are milling maps for intermetallics. This is one such intermetallic NiAl. You can see that irrespective of the impact energy of the ball, there is a minimum total energy where the initiation of the AlNi phase formation occurs, and there is a minimum energy beyond which there is a completion of the reaction. So the reaction starts and reaction completion always occurs beyond a particular energy. Similarly, there is a minimum energy beyond which complete disordering of the ordered NiAl occurs, below which the order parameter is higher than 0, and beyond that the order parameter becomes 0. So suddenly there is a complete disordering occurs, and that is again a function of the energy. And one can correlate the energy required for amorphization to thermodynamics and show that this is for amorphization. One can do similar thing for any phase formation. There is always a direct correlation between thermodynamics and the energy required for any phase formation. So one can have a strong correlations, and this is one thing which we have talked about it at some point of time. What are the criteria for some amorphization? One, thermodynamic criteria, kinetic criteria, and we have also talked about what is the strain, critical strain that is required for amorphization to occur, and we have talked about the calculated glass forming ranges, thermodynamics, and which can be compared with the experimental glass forming ranges. And this is another interesting thing. For one particular system, this is a nickel niobium system, where we are showing you what are the glass forming ranges that you can get by different techniques. You can see all these hatched ones, the big hatched ones is all amorphous composition range. So you can see that range is very small for splat quenching. Splat quenching means gun quenching, okay. And then if you do RF sputtering or laser quenching or ion beam mixing and mechanical alloying. Mechanical alloying shows you very wide composition range. So the glass forming range can be very wide. An interesting thing is also that by liquid metallurgy route, that means if you use rapid solidification, the glass formation always occurs near the eutectics, particularly near deep eutectics. Why? Because that is where liquid is stable, and that is where the TG is close to that of the TL, and that is why we have talked about glass forming criteria such as TRG, reduced glass transition temperature, that is very high at the eutectic temperature. So that means in case of nickel niobium, this is the composition, around 60% is a composition where you can easily get a glass by splat quenching. For example, you can see this is the range by rapid solidification, whereas in case of mechanical alloying there is no such restriction. You can get it over a wide composition range. And This is another criterion for amorphization, the strain criterion which we have talked about it before, and this is how an intermetallic can be made into an amorphous. We usually know if you take a system like this, you have two solid solutions on both the ends and one intermetallic at the middle, and if you draw the free energy composition curves, you can see an intermetallic has the lowest free energy. If you take the intermetallic has the lowest free energy and the liquid has a free energy like this and the solid solutions have a free energy like this, it is easy for a solid solution to become an amorphous beyond the T0 curves. If you choose this T0 curves, beyond that the solid has a higher free energy than the liquid, so you can easily get an amorphous phase. But an intermetallic, if it has to become a liquid, it is not easy because there is no direct driving force. The liquid always has a higher free energy than the intermetallic, or the amorphous phase has always a higher free energy than the intermetallic. So what do we do? What we do is, when we take such a intermetallic and start doing ball milling, what happens is you are putting so much of energy into the system, and because of the defects that you are putting, when you put so many defects into the intermetallic free energy goes up, and when the intermetallic free energy goes up, you will come to a certain condition where the free energy of the intermetallic goes beyond that of the amorphous phase, and once that happens, then suddenly there will be a driving force for the intermetallic with so many defects to transform into an amorphous phase. That is what exactly happens when an intermetallic tries to transform into an amorphous phase. And when you take a mixture of two intermetallics, let us say two intermetallics have been chosen here, one is this intermetallic, another is this, and the solid curve that you are seeing here is a free energy of the amorphous phase, let us say, and the mixture of the two intermetallics has always the lowest free energy. Now if you take the mixture of two intermetallics, again start doing ball milling, then the free energy of the intermetallics goes up, and again if you look at after some time of milling, the free energy of the mixture of intermetallic becomes something equivalent to that G3, and that G3 from G3 to G4, G4 is the free energy of the amorphous phase, there is a driving force, so now the transformation can occur. But directly from the mixture of intermetallics one cannot have amorphization, so one has to put in some amount of defects so that the free energy can go up and then transformation can happen. And one can also have amorphization in immiscible systems. An immiscible system is like this. For example, if I take a copper tantalum system, it is an immiscible system, and if I take the tantalum metal and the copper metal, the free energies are given here. The free energy of the mixture is given by this, the line joining these two free energies, and if you look at the free energy of the amorphous phase, the free energy of the amorphous phase is something like this, because it has a positive enthalpy of mixing and positive free energy of mixing. So the free energy does not go like this, but the free energy goes like this. And if the free energy goes like this, when you deform the individual metals, and depending on the type of metal, copper cannot be easily deformed when compared to tantalum. Tantalum has a higher melting point, so you can make it nanocrystalline much more easily. So as a result, it becomes finer much more easily, so its free energy goes up to a much higher level than the free energy of the copper going up. So the dashed line that you are seeing is the free energy of a mixture of the deformed metals, that means where the defects have been introduced. And if you look at that and then put in the interfacial energy into it, the interfacial energy because of the nanocrystals, whenever you have a nanocrystal you have an interfacial energy. So when you look at that overall free energy because of the interfacial energy and the defects, everything put in, then the overall free energy will be higher than that of the amorphous phase, and then you will have a driving force now for such a deformed material with a lot of defects and nanocrystals to transform into an amorphous phase. So even an immiscible system can be transformed. This is not possible by rapid solidification, and one can have amorphization by mechanical alloying below a certain crystallite size. We have seen this before. when you bring the nanocrystals below a certain size of about 10 nanometers or so, suddenly it becomes an amorphous phase, and similarly beyond a certain strain it becomes an amorphous phase. And similarly here is an example of the effect of cryomilling. When you start ball milling at room temperature, this is a cobalt zirconium, you cannot bring the crystallite size to very low level. The crystallite size is only about 10 nanometers or so when you ball mill it at 30 degrees or 60 degrees or 200 degrees. These are all milling temperatures. But if you reduce the milling temperature, do cryomilling, for example minus 85 degrees and minus 190 degrees, the rate of decrease in the crystallite size can be very fast. So as a result, you come to that below that critical crystallite size, so that amorphization can easily occur. So cobalt zirconium can become amorphous very easily. So similarly you can see, so the time required for amorphization is inversely proportional to the melting temperature. The lower the melting temperature, the faster the amorphization will occur. And this is the effect of contamination. We know that contamination is one of the major problems by ball milling, but sometimes contamination can be useful. We have talked about it at some point of time. Here contamination can lead to what is called disordering into a compound. If you ball mill NiAl into tungsten carbide, you get an ordered superlattice reflection, but if you ball mill it in a stainless steel, you will never get a superlattice reflection. That means it is completely disordered. That is because the iron goes into the contamination, the iron coming from the balls and the container, it goes into the NiAl and reduces the ordering energy, and because of which the ordered NiAl completely becomes disordered. And once it becomes disordered, it becomes ductile. And again, another last point is the temperature of ball milling. Lot of people have studied about this temperature. Initially people thought the temperature will be very high, but then later people have thought about it a lot and did a lot of modeling and also some experiments. There were some very ingenious experiments, such as taking martensite, putting the martensite into the ball mill and start doing ball milling and try to see what is the microstructure of this martensite after some time of milling. And we know that martensite gets tempered to various different structures depending on the temperature of tempering. So if we look at the tempered structure, we can find out what is the temperature of tempering. So what was the temperature during ball milling, one can find out. What was the temperature at the impact of the ball to the powder. So people had a look at that and then could see that the temperature never goes beyond about 300 degrees. So, and we did a lot of modeling and tried to measure the temperature of the Tolvin bath and tried to have an equation which correlates the actual temperature of the powder to the temperature of the bath, and we could see the temperature never goes beyond 450 Kelvin. 450 Kelvin is about 200 degrees centigrade. So you can never go beyond this. So that is a kind of the temperature raise that you can think of. So temperatures are never very high. So everything is happening more or less at room temperature. But why this kind of processes are happening at such low temperatures is because of the large diffusivities, because of the large number of defects that we are introducing, and the fine scale that has been generated because of the generation of the nanocrystals. With this we will stop.